We traditionally define transmission according to one of 4 different routes for many respiratory viruses. I'll skip over the top 2, direct contact and indirect contact, and then move directly to the bottom 2, which are relevant for airborne transmission. The first is large droplet spray, involving droplets that are large enough that if you're close to someone, they come out of one person's nose or mouth, they fly through the air like ballistically, like projectiles, like mini cannonballs, and land on the other person's eyes, nose, or mouth, their mucous membranes, and cause infection that way. Next slide, please. Traditionally, this route is defined as involving droplets that are larger than 5 microns and happening only at close range, less than 1 or 2 meters. Aerosols, or airborne transmission, involves smaller microscopic droplets that we call aerosols that can stay in the air for minutes to hours, can be transported farther than this distance and then are inhaled. Next. So these are traditionally defined as being smaller than 5 microns, and this transmission mode is thought to happen mainly at long distance, but I think that's because the only way to really prove it epidemiologically is to observe that transmission has occurred at long distance, but that doesn't mean it isn't happening at shorter distances also. Next. The 5 micron cutoff dates to the 1950s, which point back towards a paper by Wells in 1934. Although he actually never really mentions 5 microns, he identifies a cutoff closer to 100 microns. This may come from thoughts about what size can actually reach the lungs. This cutoff, in terms of how we define these different transmission routes, is not supported by modern aerosol science. And this distinction has hampered our understanding of transmission. Next. I'm going to spend some time going over terminology. There have been a lot of debates over the different modes of transmission, and I think part of it is due to differences in how different disciplines and experts in the public think about these different words. I think in many cases, we actually are talking about the same thing mechanistically. But first I'll start with airborne, which according to WHO and infectious disease experts means that a disease is considered airborne. That implies that certain types of precautions are required, including N95 respirators. And this airborne transmission is often associated with a disease that spreads like measles. In the aerosol science community, the word airborne just means something that's in the air. To the general public, airborne can convey fear and evoke fear and panic. People think of the movie Contagion, which is like Jaws, but for infectious diseases. I think what I want to emphasize here is that there are big differences between healthcare settings and community settings in terms of the types of exposures that people are going and environmental factors that influence transmission. Next. The next term I'll discuss is aerosol, which, as I mentioned, is defined by some as being something smaller than 5 microns, and WHO often refers to aerosol generating procedures as the main way that aerosols are produced. These include intubation, ventilation, bronchoscopy, things that are thought to generate large amounts of aerosols in healthcare settings. Aerosol scientists define an aerosol as a collection of solid or liquid particles that's suspended in a gas. I think when the public hears this word, they think of hairspray. Next. Droplets, according to the infectious disease community, are defined as being larger than 5 microns, and droplet precautions imply that surgical masks are required to block the spray of large droplets from landing on someone's mucous membranes. This acts as a source control and some protection also. To aerosol scientists, a droplet really is a liquid particle that's in there irrespective of size. And I think to the public, they might think of raindrops or something coming out of an eyedropper. Next. I do want to let me talk about this one also. Droplet nuclei is a term that you'll find in some of the older literature, referring to the residue of a droplet that has evaporated to less than 5 microns. Aerosol scientists wonder if this means something like a cloud condensation nuclei, which is a tiny particle on which water actually condenses to grow into cloud droplets. I don't think the public knows what this means. The debate about 5 microns as the cutoff has been dismissed as being a technicality or maybe academic. But the fact is that if we want to be consistent between how transmission actually occurs and what size is involved, we're off by a factor of 10. And I would say that this size difference, saying it's irrelevant is like saying that the size difference between a virus and a bacterium is irrelevant. But we know that that is an important distinction. Next. We'll also see the term particle, which to some people, especially virologists, refers to the virus particle itself, or the virion. To aerosol scientists, this refers to particulate matter, air pollution in the air. And to the public, this might mean a subatomic particle. Next. Rather than getting wrapped up in the size debate, I'd like to suggest that we define transmission mainly by the exposure pathway, where large droplets are sprayed onto the body, and this is a form of contact transmission. Next. And then the smaller droplets, which we'll call aerosols, are inhaled into the respiratory system. Next. This distinction is important because it drives control strategies, whether face shields will work. They'll work for large droplets, but not aerosols, and whether ventilation has any effect. Again, that does not have any effect on large droplets because they have so much momentum, so much inertia that they're not affected by ventilation, but aerosols are. This distinction is also thought to drive the infectious dose. For some other diseases, we know that if the virus makes it down deeper into the respiratory system, fewer viruses are required to initiate infection, and this can also affect severity of disease. Next. And as an aside here, I'd like to note that the physics-based cutoff between these large droplets and aerosols should fall somewhere in the range of 60 to 100 microns, which is obviously at least a factor of 10 different from the 5 micron cutoff. Next. So now I want to take a mechanistic perspective to transmission. In many studies and animal models and epidemiological studies, we observe a transmission event. So transmission occurred or it did not, but we don't actually know the path of the virus that it took through the environment to get from the infected host to the next susceptible individual. Next. The challenge is that at close contact, all these 4 transmission routes that I described earlier can be at play. Direct contact, if people are touching, for example, they're shaking hands here. We have fomites or indirect contact with contaminated objects that could be shared, passed back and forth. And the respiratory plume here shows it's actually accurate in terms of numbers and size of numbers, in that when someone speaks, they release about 100 times more small aerosols than they do large droplets. So just you can see that this large droplet shown in blue would have to travel from the infected person's mouth and land directly in the eyes, nostrils, or mouth of the other person. At the same time, there's this very concentrated cloud of aerosols, and the person opposite is going to breathe those in, about half a liter's worth of air per breath. Next. So at close contact, it's clear that transmission can occur by both droplets and aerosols, even though it has been assumed that droplets dominate. Yuguo Li at the University of Hong Kong has run a very nice physics-based model of large droplet spray and inhalation of aerosols in jets produced by talking and coughing. And I'm just jumping to the final result of his here, which is a graph showing the ratio of exposure by large droplet spray to inhalation of short-range aerosols. And this refers to the volume, total volume of droplets or aerosols that the other person is exposed to. We're assuming that the amount of virus scales with the volume of those droplets, which is a separate point of discussion. But if you read this graph, what it shows on the x-axis is the distance that the two people are apart. So we're going from 0 to 2 meters. The y-axis shows this ratio, L to S, so large droplet spray to short-range aerosol inhalation exposure. So at a value of 1, that means that those two modes are equally important. If it's greater than 1, that means that large droplets dominate. If it's less than 1, it means that aerosols dominate. And you can see that for coughing, shown in black, if the people are closer than about 40 or 50 centimeters, 0.5 meters, then the large droplets are important. But as you move beyond 0.5 meters, it's actually the aerosols that are more important. And then if we look at talking, which is important for asymptomatic transmission, we can see that the ratio is 1. That means that droplets and aerosols are equally important, only at a very close distance, about 20 centimeters. That's pretty close for my taste. But as you move farther apart, you can see that aerosols begin to dominate. As soon as you're 30 or 40 centimeters apart, the contribution from large droplets is expected to be very small, whereas aerosols would dominate exposure. Next. In addition to transmission happening at close range, it can also happen at a distance. These aerosols in the respiratory plume can remain suspended in the air for long periods of time, during which they can spread throughout the room, as shown here. We have red dots everywhere. The droplets will fall to the ground. Some of these aerosols can also settle on the ground, where they are susceptible to being resuspended into air, causing kind of a secondary opportunity for transmission by aerosols. Just as a note, indoors, maybe somewhere around half of particles in the air are actually resuspended by us just walking around. We call this the pig pen effect. Next. So I have shown that transmission by inhalation of aerosols can happen at both short and long range. And now we'll talk about why size is so important.